I think the recording's going, so I shall go myself. Hello, I'm Tim. I am a PhD researcher at Oxford. Particularly, I work in wind and marine, hence the wind turbines in this picture. And so today we're going to do some fun, a bit of maths, but hopefully something interesting and something that will captivate you. So what we'll do is I will set the scene for you. I shall let you know how wind power is currently operating in the UK, and hopefully maybe ask some questions about it and create some excitement for it. Then we're going to derive a really simple model for a turbine that you probably would derive in your first year. And it's actually the inverse of a plane propeller, which makes it a really versatile bit of maths. And using that, we'll explore what that kind of model tells us about how we maybe should be designing wind turbines and to get the most out of them. And then we'll look at some of the model limitations, and I'll discuss maybe how we get around those limitations. And as I say, this is kind of the level you might experience in your first year of engineering. So we'll kick off. And so currently, the daily power consumption in the UK is as shown in the figures. So you can see that it varies during a day. So we need to be able to meet the demand for a variable day. And but a vast majority of it's being created. So this is a day just recently, and a vast majority of it's coming from wind. In fact, over the summer, 40% of our power came from wind. And so we've got this kind of daily variation. But if we also look, and also I should note here, I've written it down there, that solar is not available during the night hours, which makes wind incredibly important at nighttime because the wind doesn't stop. And if we look at the yearly variation, well, you can see that again, renewables are doing quite well. And overall, wind produces most of our power. Again, it's actually producing more than any fossil fuel in the UK. And again, this is a very recent figure. And importantly, you can see in the variable in the year is that there's a lot stronger winds in the winter and they're a lot weaker in the summer. And that actually is really quite useful because in the winter is when solar, of course, is unavailable. I don't know and if you can look out the window right now, but it's definitely not sunny. And actually, as you can see, the demand's the highest in the winter. You're powering your house, you put the lights on, you might not be outside as much. And so wind is a really good and great renewable resource for meeting this kind of high demand we see in the winter. So, okay, the UK is doing very well in terms of wind, but you can see it's got some quite large variability in what power we need and how we produce it. And actually, if you look over the entire globe, this is a wind variability. So if it's dark red, it means that you've got really nice, strong wind. And if you've got the lighter blues, that means it's very weak wind. And what you can see is that in the regions where we are, so the North Sea is up here somewhere, and you can see that we're getting really good, strong wind, and we're quite lucky. And off the coast of America, you'd also get the same. So we're in this kind of ideal place to be harnessing this power, whilst in other places we might not be so much. And so you can see that's why this UK power trend has gone the way it's gone, which is that we are now generating roughly more wind. So this is 2024. So this is from 2012 all the way to 2024. You can see that we actually now produce more wind than any energy from wind than any other power. And that kind of led this really great decline in the emissions per kilowatt hour. And the idea I'm trying to get to you here is that we are moving towards wind. We just have to accept it now. It is the way we're going, and we're becoming highly reliant on it. And to do this, I also want to make you aware that the size of the turbines are getting vaster and vaster. We are having to design these large turbines with great farms because we need to account for more and more of our power coming from them. To give you an idea, the biggest wind turbines that we're now producing are the height of the Shard in London. I mean, we're talking 200 and something meters high. These are offshore. The inshore ones don't make half as much power. The offshore ones, you can only transport them via ships. They're that big. You can't drive them even around. You can see it on the ship down there. So here's the problem statement. I know I'm waffling around at the start, but the problem statement really is that we are becoming very reliant on wind power, and we are needing larger and larger farms, bigger wind turbines. And our energy is actually quite variable. We're demanding lots of different variability in the energy. So we need to really be able to predict how much power we're going to have. And we need to be able to actually design these wind turbines. We need to think about how do we design them? How do we design a farm? And the solution, or the solution that we think is the best way to go, is to produce kind of accurate models. These are kind of mathematical models for a wind turbine that somehow tell us how the wind turbine operates, give us some idea of how it's going to operate best, how it might work best in a farm. And then in some way, you could maybe even take in the atmospheric conditions. You could predict maybe 48 hours in advance. You know what the wind is. You can look up the weather. You can look up the wind. And so you'd be able to take a guess for how much power you're going to get in the future. So we're actually going to derive a very simple model for this in this lecture itself. I know, exciting. So I'm going to give you 2 minutes just to grab a pen and a pencil and paper. You will need them. We will be writing, but not lots. I am an engineer. So I'll give you 2 minutes to do that. I should also say that we will now use the chat feature as well in the next section. So I'll be asking you some questions, and if you can respond in the chat, that would be really great. I don't know whether you can thumbs up in this chat or anything, but if you see like someone's written something you were thinking, you can obviously give it a thumbs up to agree with that. But it will be very low key, isn't it? No big questions, no essays needed. Okay. Right, if you've got your pen and paper, we shall start. So I'm going to describe this model. So you've got some inflow on the left-hand side. You have a wind turbine in the middle, which we're going to represent through this kind of disk. And then you've got some outflow. I'm going to tell you, when we do this model, we're going to be really interested in four different positions. So very far upstream, so way away from the wind turbine, where the wind turbine doesn't have an effect. We are then going to be interested in just before we get to the wind turbine, just after the wind turbine, and then far downstream where the effect of the wind turbines felt, but it's not very in close proximity. And we'll be following these kind of what's described as sweep stream tubes. We're kind of following this fluid through the wind turbine. So my first question to you is, what quantities would I be interested in if I want to be able to solve, for example, the power or the velocity or this kind of idea through the wind turbine? What quantities would I be interested in? I've given you some examples there, but none of those are very useful. If you can put in the chat what quantities you might be interested in at these different positions. Speed, yeah, it's good. One, I'll give you a couple more minutes. I'm still missing at least 2. So power, I definitely want to find out in the end. I agree. And the speed one, yeah, velocity, very useful to know at these different positions. What else might we want to know? Is a fluid? It's air. What might be important with air? Pressure. Yeah, double. There we go. Pressure is really useful. Okay. What I mean, this is an interesting one. We're almost there. I kind of want to push to get all 3 now. What's the third quantity I might be interested in? What do you think about a wind turbine might define it's how it acts? Surface, yeah, there we go. Area. That was it. There are 3 quantities. That's all we really needed were these 3 quantities. Okay. So I have my wind turbine. it's a very simple model. Again, I'll remind you, this disk is representing the wind turbine, some kind of flow in. Something happens to the flow because the wind turbine's there. It does some energy extraction. It has some resistance to the flow. And the flow comes out the other side. Okay, so I'm going to give you an easy answer here and start off for you. The velocity, we'll call it on the left-hand side, we'll just call it the free velocity. This is kind of, if I was to go out and stand in the street, this is the wind that's going to hit me at whatever speed that is. It might be 9 meters per second. It could be 100 miles per hour. I don't know. And when you're sat in wherever you are now, the pressure you're feeling, you are actually feeling a pressure on you. It's the atmospheric pressure though. So everything's feeling this. So we know that far up from stream from this wind turbine, it's going to be feeling atmospheric pressure. And I'll just give it an area. I'll just say it's pi r1 squared, which is just a circle, the area of a circle. And we'll just call this area, this is diameter 1, so it'll be radius 1. And so we'll go to the second position. So this one was just before the wind turbine. And well, I don't know what the pressure is. So I'm going to say it's pressure 2. I know the area because it's going to be the area of the disk. So it's going to be the radius of the disk. And for the velocity, I'm going to introduce this term here. And it's going to be that the velocity at the disk is equal to whatever the free stream velocity was times 1 minus a. And I'll explain that 1 minus a bit in a second. On the other side of the disk, so this is just 2 probes just put right either side of the disk, we're going to say that the velocity is again going to be the same because they're pretty much next to each other. So this is whatever the turbine's having the effect on the velocity is. The pressure, I don't know. So I'm going to call it pressure 3. And the area, well, it's going to be the same as the area in the just before the disk, because we'll say the disk is infinitesimally small. We'll make that assumption. We'll say it's really, really thin. So we're going to get pi r squared of the disk radius. And in the wake, so we call this region the wake, it just means the bit behind the wind turbine where you get a bit of velocity deficit, so it's not quite as going fast. We'll say, well, it has this wake velocity. I don't know what that wake velocity is, but I would quite like to know it. But we'll say that we take this 0.4 far enough downstream that the pressure is now back at this kind of atmospheric pressure. It's not feeling this local pressure that you feel around the wind turbine. And again, we'll just term it as having this area, pi r4 squared. Okay, so I said I'd go back to this A idea. It's quite simple, really. It's not a complicated. It's just a constant. So it kind of is there to represent how much resistance, so how much the wind turbine is holding back against the flow, or in a sense, how much energy it's pulling from the flow. So you can see that if I had a value of, it can vary between, I should say, also can only vary between 0 and 1. So you can see that if it was 0, then the speed at U2 would be the free stream speed, the speed at U3 would be the free stream speed. And that's equivalent to the wind turbine not being there. And if it was it's called A, the induction factor. And if it had a value of 1, then the speed at U2 would be 0, the speed at U3 would be 0. And that's because it would be like a physical disk. It would be not letting any of the flow through. So all A is describing is kind of how much flow gets to go through the disk, how much resists it. It's a bit like what we describe as like a porous region. That's like a sponge. You know, how sponges have pores. If you were to pour water on it, only some of the water would come through. But if you just to pour water normally, it would all obviously come through. So that's where the A bit comes from. But it's not a particular value. You don't need to have known it beforehand. It just represents how much the velocity is going to drop. And to help you with that idea, I've kind of drawn them out in graphs for you. So position 1 was here, then we made our way and we had some kind of pressure at the turbine. I don't know what it is, but it will be a pressure increase. Then the turbine happens, then we'll have had a pressure decrease. I don't know what that pressure is. And then we return back to this atmospheric pressure. Yeah, we all saw that before. And in terms of the velocity, we went in with this free stream velocity. Then there was some kind of resistance to the flow. This is the 1 minus A idea. It was so it's going to be a fraction of, it's going to be U free stream times 1 minus A, where A is between 0 and 1. And it's going to come out at some slower velocity. I have no idea what that velocity will be right now. Okay. Next question for you. When we derive things and when we do lots of these kind of fluid dynamics, so I'm a fluid dynamicist, when we do fluid dynamics problems, but also just generally when we do these kind of physics and engineering problems, it always simplifies just to a set of conservations. And so I want you to put in the chat, what do you think you need to conserve when you've got a system? What are the physical quantities you have to conserve? Momentum, energy, yeah, these are great. There's another one. If you want, if you yeah, if someone's written something you liked and you think, yeah, that's the correct one, you can thumbs up. Yeah, great. Oh, we're on for a roll here. Energy, momentum, and mass. Easy peasy. And as I say, this is concept is basically essential to any way we derive anything. So anytime you derive anything, especially in fluid dynamics, but generally for physics and for engineering, this is how we'll solve it. So let's have a go at doing mass conservation to start with. Could anyone tell me how we might go about writing mass conservation for a fluid, for something that flows? Does anyone have an idea? Again, you can you if you do, you can put it in the chat. So I'll tell you what, I'll give you a clue. Can anyone tell me what's the equation for density? Mass divided by volume. Yeah, yeah, mass over volume. This is good. Okay. So therefore, if I want mass, I just have to do volume times density. Right. So I definitely can have density because yeah. So volume times density equals mass. Yeah. So I've got a fluid. So I definitely have density. Volume is a bit harder though because this thing is continuously moving. But we did talk about a quantity I might be interested in earlier, which is the area. So how might you get the how do you think maybe you could get the volume and the velocity to pair up to get this kind of mass? Area times velocity times time almost. I will relinquish. These are really good ideas. This is a hard one. So we describe it as something called the mass flow rate. So instead of just purely conserving mass, we're going to conserve it at a rate. And so that comes out as the density times the area, which times velocity, which you can kind of see links back to mass, how we've just gone through it there, where we've said, oh, it's mass divided by volume is density. So what we're actually wanting to conserve is density times area times volume. And so if I want to say, well, point one, when I'm here, well, the mass flow rate here should be the same as the mass flow rate in the middle. It should be the same as the mass flow rate at the end. That's what conservation means. So if you now think, okay, let's write out this, and I'm going to assume that we're incompressible, that means that the density won't change. I mean, I'm not doing anything to it such that the density will change. I can drop the rho term. Then all I'm conserving is velocity times area. So, and I said before, we've got this free stream velocity times an area. It's going to equal some kind of velocity, which we termed before, times an area. It's going to equal a wake velocity times an area. So that's these 3 points, the middle point, the start point, and the end point. So I'll give you like 30 seconds to kind of write this equation down and then have a look and try and piece the two together. Okay, so I'm hoping you all at least managed to roughly write this down. I will bring up the equations back again later, but maybe at least you got your head around this idea, this mass flow rate instead of mass. But if you kind of just accept that for now, and you can see how this is the left-hand side, this is the middle, and this is the end, and it's being conserved as we go through this wind turbine. The turbine doesn't take mass away. You're not missing stuff because the turbine was there. And then I want to do momentum conservation next. And I've kind of given you the equation there for momentum. So I think most of you will know it as just mass times velocity. That's what, the classic case I suspect you'll have seen, two snooker balls getting hit and one interacts with the other, or two bowling balls, and that's your mass times velocity. But in fluids, you can often rewrite it as pressure times area, because you remember that, well, force is pressure divided by area. Essentially, you can work this through. You'll realize that the units for pressure times area are the same for mass times velocity, which would be kilograms meters per second. Okay, and so we'll go back to this control volume. Again, we want to conserve now momentum. And I promise you this is going to help. We are doing lots of small things here that are going to come together. So between points 1 and 2, can you tell me, do you think momentum's conserved between the start and where the disk is? Just again in the chat if you want to. Just conserved or not conserved? There we go. We've got a yes. And yes, it is conserved. So there's nothing between the start and just before the disk. So there's nothing to have taken any momentum out of the system. Now, the wind turbine actually does. It's an energy sink. It acts as an energy sink. So momentum is not conserved over the wind turbine itself. So then we can say just after the wind turbine here, I hope you all can see my mouse. Can someone just give me a yes to say they can see my mouse? Great. Just on the other side of the turbine and to the outlet, again, momentum will be conserved. There's nothing between those two regions. And so we can say that the difference in momentum over the wind turbine itself, so between just before and just after the wind turbine, is going to be the same as the difference in momentum between the start and the end of this entire control volume. Okay, so that's the difference here is going to be the same as the difference between points 1 and 4. As I say, yeah, momentum is constant either side. And the change in momentum, so this is written down just in case I was very bad at explaining it, is equal to that over the entire disk is equal to that over the entire domain. And so using this, so I'll describe it through. So here, the left-hand side, I've used pressure times area way of describing the momentum. And I'm telling you, I've done it this way for convenience. It's going to work out better. So we use the pressure times area way on the left-hand side to find the difference between either side of the disk. And I've used the momentum in terms of the mass times velocity, but here we'll use mass flow rate times the velocity. And I've used that to get the momentum difference between the start and the end of the entire system. But equivalently, they're the same. They're just the change in momentum. Okay. And I'm going to simplify what we're doing here. So we said that the mass flow rate before, so if I skip back, I'll tell you what, I'll skip back. There we go. So we said the mass flow rate before is equal across the whole thing. So I know that if I have the mass flow rate of one position, it's equal to a different position. And so I can say that, well, although it might be the mass flow rate at the end and at the start, it's actually always going to be equal to the mass flow rate in the middle. So that's all I've done here is I've just taken this generic term for mass flow rate and put it all about the stuff that's going on in the middle around the disk. So it's the mass flow rate here is that's the one. And then I've just simplified this to just be U free minus U wake. So if you write that down, and yeah, I've chosen a convenient mass flow rate, it will help us in the long run. And the reason why is because you can quickly then cancel out these areas. You can see how we've got pi r disk squared and pi r disk squared. So I'll give you a second to write that down. So this is the second useful equation that we're going to have. And if you put a Y in the chat to let me know you've had a chance to write it down, and I'll move on. Great. Wait 30 more seconds and then I shall power on. Okay, so the final thing was this energy conservation. Okay, so I'm not expecting any of you to know this, but energy in a flow can be described through what's called the Bernoulli equation. And the Bernoulli equation is split up into three terms. Can anyone tell me what the leftmost term would be? Just quickly in the chat. What does it look like? Kind of energy. Yeah, it's the kinetic energy of the flow. We're having to use density here again because we're looking at a mass flow rate. I'll give you the second one. This is called the static energy. It's the static pressure, but you can think of it as almost like an energy. And can anyone tell me what the third one is? So I kind of expect you to know this one as well. Yeah, gravitational energy, the idea of lifting something up high and you have a height change. So together you can think of this as kind of the energy equation and therefore be some kind of energy conservation. And again, as we're conserving, as we've done for all the previous occasions, we'll set one equal to the next, to the next, to the next. But we know that the disk itself, so the wind turbine, this disk in the middle, is going to take some energy out of the system. So we actually know that only between points 1 and points 2, so far upstream and just before the wind turbine, well, it's going to be conserved there. And either on the other side of the wind turbine, it's also going to be conserved there. But over the wind turbine, it's not, because the wind turbine itself is taking out energy, and that's actually what we want to calculate in the end. So we don't have that value, and we won't have that value. And the other thing, I'm going to make our lives really easy. I'm going to say there's no height change. There's no height difference for this fluid overall. So from the equilibrium. So really it simplifies just into this half rho u squared plus p static. And so we can derive these two equations again. So this is from that initial one where I gave you all of the different values at the different points. Well, I said, well, it's half rho u as the free stream, it's the kind of far upstream velocity squared, kinetic energy at the start, plus, well, it's the atmospheric pressure. It's what you and I are feeling. Then just before the wind turbine, it's now at this special velocity, which is less than the initial. And it's plus some kind of pressure. We don't know what it is. That's what we'd like to find out. And on the other side of the disk, we start off again with this kind of special velocity, which is less than the free stream velocity. And so we get the kinetic energy from it, plus an unknown pressure, P3, don't know what that is. and it's equal to downstream, down in the wake, is equal to, again, the velocity, we'll call it u wake, don't know what that is, half rho u wake squared, kinetic energy, but it's going to be atmospheric pressure again. So again, I will give you 1 minute just to write these down and get them into your head and look over them again. I will remind you that equation 3 is to do with energy being conserved between the start of the wind turbine. And equation 4 is to do with energy being conserved after the wind turbine. And I will give you 30 seconds to write those down. And again, put a Y in the chat and thumbs it up. You seem to be quite good at doing that, to let me know you've done it. Okay, great. So, in case you haven't managed to write them all down, I'm going to give you a summary of equations, which is we had this mass flow rate conservation, equation number 1. We had this, gosh, I have to remember myself, pressure, momentum conservation. So you've got pressure on the left-hand side, because that was the other way we derived momentum, and a velocity way of deriving momentum on the right-hand side. And then we had equations 3 and 4, which we will simplify now quite quickly, but they were to describe how energy was being conserved. And I've rewritten equations 3 and 4 slightly for you, so you could maybe see a clue for what we might do. Can anyone guess what we might want to do with equations 3 and 4 to make our lives easier? If you put it in the chat, if you have any idea is okay. Okay. I don't blame you for not wanting to. We're going to take one off the other. That's it. You can kind of see how they're sharing quite a lot of terms here. And you can see how the left-hand bit here, these two terms, they're shared between the equations. They're both sharing the pressure atmospheric. So what you can actually do, take one from the other, and you'll end up with P2 minus P3 is equal to the difference in their kinetic energy. So the difference in their static is equal to the difference in their kinetic energy. And you can see the reason why we've done that is you look at equation 5 and then look at equation 2. We never needed to know pressure 2, and we never needed to know pressure number 3. We can just substitute one into the other. It makes our lives a lot easier. So I'll give you, again, just quick time to write equation 5. So that's, again, it's just equations 3 and 4 subtracted from each other will give you equation 5. I'll just check. I might have it on the next slide anyway. Yes, I have it on the next slide. So I have it here. This was equation 5. The difference in pressure is equal to the difference in kinetic energy. And we had equation 2, which was to do with our momentum conservation. I would say the reason why we had the mass flow rate was we've actually already used it in the equations. We've already simplified our lives a bit. And so we can combine equations 5 and 2 again, because you can see that P2, P3 is the same on both sides. I don't know why I've capitalized one and not the other. And you can show that the velocity in the wake is just going to be 1 minus 2a, this induction, so that'll have a velocity, have a value between 0 and 1, times whatever's coming in. So kind of like magic, we now know everything about this entire system based on the inflow velocity and A, which is a function of the wind turbine itself. So it's how we design it. So it will come with an A, an induction factor. But now you've got this inflow velocity. It'll have some reduction, 1 minus A amounts, and then it'll have a 1 minus 2A amounts downstream from it. Okay, so this is kind of the first solution to this useful model, but it's not the most useful solution. We'll move on to what actually comes really usefully out of it. Does anyone have any questions at this point, just in the chat, just anything you want me to go back to or go over? Great. Okay. And if you don't follow any of the maths, it's fine. This will be available afterwards. And actually, all I want you to remember is that we got to these kind of 5, 2, and 6 equations. That's what we managed to derive. We managed to derive something in terms of pressures, something in terms of velocities, and we managed to get the free stream velocity so it propagates through. So you're not having any variables you don't know anymore. So what's really useful to know from a wind turbine is power. It's what I talked to you for the first 5 minutes about was power generation in the UK. But I'm going to go back and we're going to think, okay, so how do I find power? We know pressure is force divided by area. Does anyone know what a very generic equation for power is in this kind of remit of force times something? Force times velocity, FV. There we go. Got it. Energy over time, yeah. So yeah, because distance divided by time is velocity. So force times velocity is going to be the same as exactly. You all got it. This is really good. Okay. So the energy over the disk is going to be, well, we get pressure times area, pi r squared. I'm sure you can all see this now. Force times velocity. So the velocity is the free stream times this one minus a idea times an area was pi r disk squared. And change a difference in pressure. So the energy change, so the power extracted will be the change in energy or the change in power over the disk. And we've shown previously that we can write P2 minus P3 as this rather awful looking equation, but we could write P. So we sub in how we've shown we can write P2 and P3 in terms of these, and we know that the free stream is the wake velocity is a function of the free stream velocity. Then I promise you, and I really don't expect you to derive this here, but that the power pops out for a wind turbine disk as being a function of 2 times the density, or density is constant, so that's not really going to matter, but times the area squared times the free stream, so the wind velocity cubed, that makes sense. How much wind's coming in, that's going to dictate how much power you get, times something that describes how resistive the wind turbine is, how the wind turbine's built, A, and a function of A1 minus A squared, but it doesn't matter. But you can see that the power comes out. And maybe this is something you can derive later, but you can show that this just simplifies down. So we're almost there. So that power, there we go at the top. And a power that's just available in the air based on this kind of energy equation is just a half rho times u cubed free. So the free velocity cubed times 2. So this is just how much available was in the air. So if we divide up how much we actually get from the air, so it's based on this A1 minus A squared from how much was available, we'll get its power coefficient, or the kind of the efficiency of the system. How good was it compared to what it could have had? So you have 10 things, you only got 6, well then you're only 6 out of 10 is good at getting it all. That makes sense. And actually, really nicely, you can cancel bits out. You can cancel the areas, you can cancel the free streams, and you end up showing that the power coefficient for a wind turbine, so how efficient it is based purely on this A. So how it's kind of designed. So its induction factor, it's 4A1 minus A squared. So we'll take these 2 equations, we'll think about how do we get the most power and how do we get the most efficient turbines, because that's what we really need. Can anyone come up with any ideas of, from these equations, how you might go about making the most powerful or the most efficient wind turbines? And just put it in the chat. So I'm primarily thinking about kind of which variables in these equations could you maximize to get the most power out. Surface area, yep, that's one of them. That's exactly it. Yeah, you can see how that area comes into that power equation. I had a slide. There we go. These are the two equations I want you to think about. So we've got surface area. This is a great one. Can anyone else see something in these equations that you might think about? What might we optimize? Velocity. Yeah, these are great. These are perfect. Location, windier places, higher velocity. Yes, this is exactly it. So I had this same thought myself. And I thought, okay, so power. Right, so it's the area is in there, the radius squared. And actually you can see this exactly, that the power of them has increased. There's the shard on the right. They're bigger than the Eiffel Tower, if you're wondering. And so we're working on these 15 megawatt ones that go offshore. And so that's one way we can maximize power. So we've used that equation to see that. Okay, this is the second one. Someone said velocity. Yeah, so we know that, so this is taken, so this is actually where there is now a farm, a big wind farm. This is the data taken from it. And you can see over the year, you get this high variation in velocity. So, and because it's cubed, the impact of it is massive. You know, so if you get 2 meters per second, well, it's going to be 8 meters, 8, we'll come into that equation. So you can see how that gets cubed up. The differences get cubed. So knowing there's good wind speed is really useful. But actually, the other thing to think about there is that, well, from this, we can show that, well, when you think about wind droughts, if you know, it's not windy all the time. In fact, there was this time a few years ago, I think it's 2021, you can see here, where we had this wind drought that went all across large parts of the UK where the wind farms were. And in fact, we didn't get any power out at all. And this was a really large problem. It turned into a whole PhD here. And it can happen. So we have to think about maybe spreading our wind turbines around the country because we know that their power is going to be based on the velocity. And we need to think also, therefore, about their spacing. So what happens if I put one behind the other? This is a classic photo you might have seen online. It's of the Horns Rev wind farm. And you can see how one wind turbine has a wake, so a velocity stream behind it, and it's impacting the velocity, impacting the turbine behind it. And so we might want to think about how we space them so that we can maximize that inflow velocity, which we showed before was directly linked to the power. And so people come up with these kind of crazy ideas, and they do test them and they simulate these of like, can we put them all at different heights? Can we orientate them in different directions so that their effect on each other is minimized because we know that that velocity is cubed when it comes into power, so it's really important. And there was this final little bit, and it was this A1 minus A, and I understand if you're struggling to follow what it is, but it's the induction factor. It relates to how we design it. And if we quickly plot it out, we said A can take a value between 0 and 1. So it's either the disk isn't there or the disk is there, and that's 0 to 1. If you actually plot it out, you'll get the kind of maximum power produced, not at 1 or 0, but in the middle. And this is called the Betz limit. And in fact, it's actually also where the wind turbine is most efficient, because we said the wind turbine efficiency is going to be 4A, 1 minus A squared. So it's power coefficient versus A is in exactly the same place. So at an induction factor, we'll only get the efficiency of a wind turbine is capped at being 60%. It can only get 60% of the energy out of the wind. It cannot get more. And we need to design these wind turbines to be best. So we want them to operate at that design point. We want to get all 60%. We don't want to be operating when we're only getting 30% out of it. But how do we achieve this? Well, so you can alter the design of the wind turbine. So these are lots of different ones that have happened over time and are still happening. You see, you get these 2 blades, 3 blades, 4 blades, and these tip speed, that just means how fast it's spinning. And you can see that your power coefficient, depending on which design you choose, you're getting closer to this 60%. So how we design that disk, so we've called it a disk, but how we actually design what goes in that disk. has quite an impact. And as you can see, that impacts the power and it will impact the efficiency of the turbine. We can think about the blade shape. So how, on a granular level, how does the blade actually design? How does it twist? How does it shape? How does it take the most energy out of the system? How does it minimize drag? You can derive that from that equation. You can see that from the equation. That induction factor is really important. And we can think about long-term performance for the wind turbine. So sure, we designed it really well now, but how about in 5 years' time when the leading edge on it here has degraded and they're having to spray coats on it to keep its quality good? So these graphs on the left-hand side is capacity factor. Essentially it operates at the best on the left-hand side, and over the years it reduces in capacity. It can't produce as much power. And again, this becomes a real problem when we think about powering the entire grid on renewables. So we've kind of seen how, from our model, we could maybe take a guess about how we might design wind turbines and wind farms and positions best. So that was kind of improving the velocity, improving the design, so A was better. And, I can't remember the first one. The size, increasing the size of the wind turbine. And I should also note with the size thing, you then have problems with kind of loads. So you think a moment is force times distance. So if you've got really tall wind turbines, they're actually putting enormous loads on their bases. So we can't just infinitely make them huge, sadly. But let's think about what was the problems with our models. Does anyone have any idea with this very simplified model, what might be some of the problems with our wind turbine model we solved? The turbine spins, exactly. That actually is one of the big problems with it. Yeah, it's not just a disc. Okay, I'll go off that one. As is actually a really good point. So we assumed that we only had this kind of effect in the streamwise direction. We only talked about velocity that went this way, but the turbine spins, so it actually acts on it in the tangential direction as well. And you can see this. So this is kind of this. They've added like a little bit of smoke or something at the end of the wind, at the tip of the wind turbine, so you can trace it around. You can see how it's not just going like this, not going in a straight direction. It's turning. It's getting some spin on it, and that will affect its performance. It's not just a drag. These kind of tip vortices and the way the entire wake, so this region behind the wind turbine is a little bit more complex than just saying it's a velocity at the wind turbine and it's a velocity later on and it's only going to be in the streamwise direction. You get these things called tip vortices, and the way they break down and the way that the wind turbine wake recovers is not really described in that model. And the problem with that model is I have no idea how far I can space my wind turbines apart, because it doesn't tell me the rate at which it recovers. We don't know from that. And it doesn't tell me kind of what impacts this recovery, because it doesn't account for that. It doesn't think about where does the momentum come from? How come there is not just a deficit indefinitely behind it? It's not just going to be a lower speed behind it. It will eventually recover back to that initial speed. And where does that momentum come from? And do things impact how that momentum comes down? And that's really important when we want to model things like a farm. So this is actually a simulation of a farm, and you can see all these little dots are actually wind turbines. And so how they interact with each other just can't be described with that initial model currently. And I've written down some other problems. So this is a classic one. We assumed it was a disk, a solid disk, that the resistance it presented to the flow was continuous. It is not continuous in reality. The flow will not act like that. It won't recover in the same way. We assumed it was inviscid. We didn't have any viscosity terms in there. So you know how honey is really hard to pour. That's because it's very viscous. And so we don't have any viscous energy losses. We don't have anything on those terms, no shear stresses. And it assumed this kind of clean, uniform inflow. I said, oh, it's just U free stream. That doesn't exist out in the sea. It varies with height, and it varies with time. And yeah, as I say, we kind of assume this constant force over disk. Not only was it a porous disk, but it was a constant A. So I said the induction factor, oh, it's just A. The A will vary, and in fact, you can work out that A, depending on which bit of the blade you're on, will actually vary. And so designing for a particular A is very hard. You have to design the entire blade for that particular induction factor. And so that's when you start coming up with these different shapes and designs. But there are some solutions. So these are from some of my simulations. So you can apply the model into a simulation with actual wind flow. So we use the same maths, but we now apply it to a model which actually has air in it that we're flowing over it. And we can see how it develops downstream, how it recovers. And that's much more useful when we start putting these tangential forces in. And yeah, we can make a variable in the azimuth. So that's theta, the turning theta, and the radial, so that's out from the center outwards. In those directions, we can start to vary this induction. And we actually then start to describe it in terms of lift and drag, and how the aerofoils which make up a blade, so the bits that make up a blade have a certain lift and a certain drag, and how varying their angle will impact this induction factor. And you can, instead of doing it as a disk, you can model the turbine in terms of lines, and so it's called actuator line method. And you kind of do these rotating lines that apply force in a rotation. So it's not, fluid won't continuously feel the force, it will feel it every so often as it rotates around. So in summary, we managed to derive a simple model that you might derive in your first year here, which describes the performance, in a sense, and the power of a wind turbine. But actually, you can inverse that model, as I said at the start, to describe the performance of a turbine propeller for an aircraft. It's the same dynamics. And we kind of used that to explore how kind of deriving a simple model might inform, at least to start with, some design choices and some planning we might go about for wind turbines and wind farms. And we also looked at how these kind of models are limited, and I've given you a couple of solutions to this, and how we don't just use that very basic disk model. So I will now have time for questions if you have any questions, or if you want me to go over anything, I can go over anything again, that's fine.